So, welcome back to the AI Math Club, and I hope you found last week's session on derivatives insightful. Because today we take the next logical step by exploring partial derivatives. What happens when a function's output depends on more than one input? How do we measure change then? We will break down this concept using simple terms and analogies, see how to calculate partial derivatives by hand, and of course with Python's SymPy library. Revisit the important idea of the gradient and connect it all back to how machine learning models learn. But before we start, I'd like to mention and remind that it's a super friendly and inclusive space. We promote a warm and respectful environment for everyone. Lift each other up is much important in our community. So, please maintain a professional and only friendly attitude. If something doesn't feel right, let the host know during the event or reach out via email. We are here to make sure everyone feels comfortable and included. And of course, you can find QA session. Feel free to send here any questions. This event session will be recorded. So, let's start, and here's our plan for today's session, but it will be not so long. First of all, we will quickly recap the main idea of regular derivative from last week. We will introduce functions that depend on multiple inputs like f of x, y, and visualize one. We will explain the core concept of partial derivatives using a simple analogy. We will learn the spatial notation used for partial derivatives involving the partial or del symbol. We will practice calculating partial derivatives for simple functions manually. Then we will see how SymPy makes this easy in Python. We will revisit the gradient, understanding it as a vector, but from partial derivatives. Also, we will visualize the gradient on a contour plot using, of course, Matplotlib. We will discuss exactly why the gradient is so crucial for training machine learning models, and of course, summarize, suggest practice. Let's start. And first of all, let's quickly recall last week. We learned that the derivative f prime of x tells us how fast the function's output f of x is changing at the exact moment the input is exactly x. It measures the instantaneous rate of change with respect to that single input variable x. Geometrically, we saw that f prime of x gives us the slope of the line that is tangent to the function's graph at this specific point. It tells us how steep the function is right there. But what if the output depends on more than just x? In the real world, and often in artificial intelligence, a result usually depends on multiple factors or inputs. We write this as z equals f x, y, or with even more variables. Think about the height of a hill. It depends on your latitude and longitude, two inputs. The temperature in this room depends on your x, y, and z coordinates, three inputs. A company's profit depends on how many items they sell and the cost to make each item, at least two inputs. When we have two inputs, for y, determining an output z, we can visualize the function as a surface in 3D space. Like the examples plot shown for z equals x squared plus y squared. This code uses NumPy mesh grid to create a grid of xy points and then calculates the corresponding z value using our function. Matplot 3D it used to create exactly this 3D plot, and AX plot surface draws the actual surface. And if we run this code, we will see the shape here is like a ball. Now, how do we measure the slope on such a surface? If the output z depends on both x and y, how do we talk about its rate of change? A change in x affects z, and a change in y affects z. We need a way to isolate these effects. The solution is the partial derivative. The core idea is simple: to find the rate of change with respect to one specific input variable. We pretend all the other input variables are just fixed constants for a moment. Let's use the hill analogy again. Imagine you are standing at a specific spot, xy, on the hill z equal f of xy. The partial derivative is specific to x, uh, written a symbol next, answers. If you take a teeny step only in the x direction, say due east, what is the slope of the hill right under your feet in that specific direction? You are holding your y coordinate north south position fixed, and the partial derivative with respect to y, if starting from the same spot, you take a teeny step only in the y direction, say due north. What is the slope of the hill in that specific direction? You are holding your x coordinate east-west position fixed. So partial derivatives break down the overall change into components along each input axis. We use a special symbol for partial derivatives to distinguish them from ordinary derivatives, which used this curly symbol, often called partial or del. When you see partial f, partial x, or you can read as del f, del x, it means you need to find the partial derivative of the function f with respect to the variable x. The crucial rule is when doing this calculation, you must treat all other variables like y, z, etc. as if they were fixed constants. And similarly, partial f, partial y, or del f, del y means find the partial derivative with respect to y. In this case, you treat x and any other variables besides y as constants. Essentially, you focus on one variable at a time and apply the normal differentiation rules to it while the other variables just sit there like numbers. Let's practice calculating partial derivatives manually for a couple of simple functions. Remember the golden rule. Treat all variables you are not differentiating with respect to as constants. Example 1, as you can see, where f of x y equals 3x squared plus 5y to the fourth. To find partial f partial x, we treat y as a constant. And the term 5 of 5y to the fourth is therefore just some constant number. The derivative of 3x of squared with respect to x is 6x using the power rule. The derivative of the constant term 5y to fourth with respect to x is 0. And to find partial f partial y, we treat x as a constant, and the term 3x squared is just a constant number. Its derivative with respect to y is 0, and the derivative of 5y to the fourth with respect to y is 5 multiplied 4y to the 3 and equals 20y to the 3 using power rule. And example 2 is interesting also. And let's f of x y equals 7xy. To find del f and del x, treat y as a constant. So 7y is just a constant multiplier attached to x. The derivative of x with respect to x is 1. And therefore, del f del x equal 7y multiply 1 and equal 7y. To find del f del y, treat x as a constant. So 7x is a constant multiplier attached to y. The derivative of y with respect to y is equal. Therefore, del f del y equals 7x multiply 1 and equals 7 times x. Once you get the hang of treating the other variables as constants, is just applying the regular differentiation rules you already know. Just like with ordinary derivatives, we can use sim_pi to compute partial derivatives symbolically, which avoids manual calculation errors. We use the same function sim_pi .diff as before. The key difference is that we now specify which variable we want to differentiate with respect to as the second argument. sim_pi automatically handles treating all other defined symbols as constants during the calculation. For example, let's take a look at this code. We first define x and y as symbols. For our first example function, 1, which equals 3 times x squared plus 5 times y to the fourth. And as you can see, we can calculate quickly. And thanks to sim_pi, directly applies the rules for us, making it very convenient for finding partial derivatives. Now let's revisit the gradient, which we introduced briefly last week. The gradient, written as nabla f or grad f, is simply vector that packages together all the partial derivatives of a function. For a function of two variables, where f of x, y, the gradient is the vector nabla f, which equals the vector partial f, partial x, partial f, partial y. Thanks of it simply as a vector whose components tell you the slope of the function in each primary input direction at a specific point. The first component is the slope purely in the x direction. The second is the slope purely in the y direction, and so on if there were more variables. The most important property of the gradient vector is that it always points in the direction where the function f is increasing most rapidly at that point, the direction of steepest ascent, like pointing straight uphill on our hill analogy. The length or magnitude of the gradient vector tells you how steep that uphill slope actually is. Let's visualize the gradient again, this time for a slightly different function. F of x, y equals sine x plus y squared divided by 4. As you can see from the example, the code first uses sim_pi to define the function using sim_pi.sine and find the partial derivative symbolically. Partial f, partial x, or del f, del x, which is cosinus x, and partial f, partial y, which is y divided by 2. It then uses sim_pi dot lambda to create numerical versions for plotting. It sets up a grid using numpy.meshGrid calculates the function value z across the grid and calculates the specific gradient vector components grad x, grad y. At the chosen point, x equals pi divided by 2, y equals 1. The plotting code uses plot plt.contour to draw the contour lines of equal height, and plt.quiver to draw the gradient vector as a red arrow starting at the red point. If we run this code, so we will see the next plot. Look at the contour plot. The lines show where the function has a constant value. The red dot is our point, pi divided to 1. The red arrow is the gradient, our nabla f, at that point. Notice again the gradient arrow points uphill across the contour lines toward higher function values and appears to be perpendicular to the contour line it originates from. This visually reinforces that the gradient shows the direction of steepest ascent. Now, why is this gradient concept so fundamental to machine learning? Think about training a typical machine learning model, like a neural network. The goal is to adjust the model's internal parameters, its weights, Let's call them V1, V2, V3, etc. And biases, let's call it B. So that the model makes good predictions. We measure how bad the predictions are using a cost function or loss function. Let's call it Y. This cost yacht clearly depends on the values of all those parameters. Yacht V1, V2, V3, and etc. and B, our biases. Our goal is to find the parameter values that makes our yacht as small as possible, uh, minimum cost. How do we do that? We use an algorithm like gradient descent. The core idea is to figure out how the cost yield changes if we make a teeny adjustment to just one parameter, say V1, while keeping all other parameters fixed. That's exactly what the partial derivatives, partial yacht, partial V1, tells us. We calculate this for every parameter. The gradient nabla yacht is simply a big vector containing all these individual partial derivatives. This gradient vector points in the direction in the high dimension space of all possible parameter values that would increase the cost yacht the fastest. Since we want to decrease the cost, gradient descent takes a small step in the direction opposite to the gradient minus nabla yacht. By uh, repeatedly calculating the gradient and taking small steps downhill, the algorithm iteratively finds parameter values that minimize the cost function, making the model better trained. So partial derivatives allow us to handle functions with potentially millions of parameters and figure out how to adjust each one to optimize the overall outcome. Let's summarize week 10. So the functions can depend on multiple input variables. The partial derivative, like partial f, partial x, measures the rate of change with respect to just one variable, treating others as constants. It presents the slope in that specific input direction. The gradient, nabla f, is the vector containing all the partial derivatives. Crucially, it points in the direction where the function increases fastest, steepest ascent. This gradient is essentially for machine learning's gradient descent algorithm, which minimizes cost functions by moving in the direction opposite to the gradient. We learned that SymPy's diff function easily calculates partial derivatives symbolically, and Matplotlib helps visualize the concepts. So we don't need to do this manually. To help solidify these concepts, there are some practice exercises and resources for further study. As a thought exercise, relate the gradient back to the hill analogy or a real topographic map. Which way does the gradient point? The resource like links point to Han Academy's multivariable calculus section, the SymPy tutorial on derivatives, and of course Matplotlib documentation. Getting comfortable with partial derivatives and gradients is really key for understanding machine learning optimization. To practice these important concepts, please review the concept of partial derivatives on Khan Academy. Try manually calculating And remember the rule, treat the other variables as a constant. Use SymPy to check your manual results and to find the partial derivatives and the full gradient vector nabla f. For the more complex example involving SymPy cosine, practice evaluating the gradient vector at a specific point using SymPy's SUPS method. So that brings us to the end of today's session. Thank you all for your participation. It was great to have you all here. If you have any questions at all, don't hesitate to reach out on our community Discord channel. This session was recorded and will be available later on our GDG Ahlen YouTube channel. So I'm really appreciate if you could take a few minutes to fill out the post-event feedback form. Uh, it's really your feedback is invaluable in helping us improve and make future sessions even better. Once again, thank you for joining and see you in our next session next Sunday. Until then, keep learning, experimenting, and of course, building with AI.